This presentation covers Chapter 13, Magnetic Effects of Electric Current for CBSE Class 10 Physics, Index. The presentation will cover the following topics: magnetic field and field lines. Magnetic field, due to a current-carrying conductor force on a current-carrying conductor in a magnetic field. Electric motor, electromagnetic induction, electric generator, domestic electric circuits. Introduction. The term magnetic effect of electric current means that an electric current flowing through a wire creates a magnetic field around it. This can be observed when a compass needle deflects when brought near a metallic conductor with a current passing through it. A magnet is an object that attracts materials like iron, steel, nickel, and cobalt. Magnetic field and field lines. Magnetic field, the region surrounding a magnet in which the force of the magnet can be detected, is said to have a magnetic field. The magnetic field is a quantity that has both magnetic and direction. As such, it is a vector. The term is used for two distinct but closely related fields denoted by the symbols B and H, which are measured in units of Tesla and ampere meter, respectively. In the SI, is most commonly defined in terms of the Lorentz force it exerts on moving electric charges. Characteristics of magnetic field. The characteristics of magnetic field are: the relative strength of a magnetic field is shown by the degree of closeness of magnetic field lines, i.e., the greater the number of magnetic field lines in a unit space, the more the strength of the magnetic field. The strength of the magnetic field at a given point depends upon its distance from the pole of a bar magnet, i.e., the more space, the less the strength of the magnetic field. Magnetic field lines, te keerfeit lines along which te ironfilling allegens or te pate along which te freelei before het magnetic needle moves are telle te field lines or magnetic lines of force. Te direction of the field is taken to be te direction in which a noordpole of the compass needle moves incident. Characteristics of magnetic field lines. Magnetic field lines have the following properties. They are closed curves. They appear to emerge from the North Pole and end at the South Pole outside the magnet, while running from south to north inside the magnet. Magnetic field lines repel each other. Critically, no two field lines ever cross each other. If they did, a compass at that point would have to point in two directions at once, which is impossible. Magnetic field due to a current-carrying conductor. When you place a magnetic compass nearby the current-carrying wire, the compass shows the presence and direction of the magnetic field around a straight length of the current-carrying wire. The current through a wire produces a magnetic field. The shape of the magnetic field, lines for a straight conductor, is concentric circles. These concentric circles become more extensive as we move away from the wire, magnetic field, from a straight conductor. This slide illustrates that when the direction of the current in a straight wire is reversed, the deflection of a nearby compass needle also becomes opposite. This demonstrates the direct relationship between the direction of the current and the direction of the magnetic field it produces. Visualizing the magnetic field. A magnetic compass shows the presence and direction of the magnetic field around a straight length of current-carrying wire. The current through a wire produces a magnetic field. The shape of the magnetic field lines for a straight conductor is concentric circles. These concentric circles become larger as we move away from the wire. Right-hand thumb rule. The right-hand thumb rule is a method for determining the direction of the magnetic field around a current-carrying conductor. It is a convenient way of finding the direction of the magnetic field associated with a carrying conductor. Imagine that you are holding a current-carrying straight conductor in your right hand such that the thumb points towards the direction of the current. Then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field, as shown in Fig. This is known as the right-hand thumb rule. Application of the right-hand thumb rule. Question: a current flows from east to west in a horizontal power line. What is the direction of the magnetic field at a point directly below it and directly above it? Solution: applying the right-hand thumb rule. The current is in the east-west direction. Applying the right-hand thumb rule, we get that the direction of the magnetic field at a point below the wire is from north to south. The direction of the magnetic field at a point directly above the wire is from south to north. Magnetic field due to a current through a circular loop, when a straight wire to form a circular loop and pass a current through it. Here, the concentric circles around every point of the circular loop become larger as the distance from the wire increases. Properties of the magnetic field due to current in a circular loop. The magnetic field lines are nearly circular where the current enters or leaves the cardboard. Within the space enclosed by the coil, the field lines are in the same direction. Near the coin's center, the magnetic lines are almost parallel. Thus, magnetic field near the center of the coil may be considered uniform. More properties of the magnetic field in a circular loop. At the center of the coil, the magnetic field is perpendicular to the plane of the coil. If the circular coil has n turns, the magnetic field produced is n times stronger than that of a single turn, because the fields from each turn add up. Magnetic field due to a current in a solenoid. A solenoid is a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder. The pattern of the magnetic field lines around a current-carrying solenoid looks similar to the pattern of the field around a bar magnet. Solenoids and electromagnets. One end of the solenoid acts as a magnetic north pole, while the other acts as a south pole. The field lines inside the solenoid are parallel straight lines, indicating that the magnetic field is uniform, the same at all points, inside. When a magnetic material like soft iron is placed inside a current-carrying solenoid, it becomes a strong magnet. This is called an electromagnet. Force on a current-carrying conductor in a magnetic field. Electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on the magnet placed in the vicinity of the conductor. The magnet also exerts an equal and opposite force on the conductor. Marie Ampere suggested that the magnet also exerts an equal and opposite force on the current-carrying conductor. Fleming's left-hand rule. Fleming's left-hand rule is used to find the direction of the force on a current-carrying conductor in a magnetic field. To apply the rule, stretch the thumb, forefinger, and middle finger of your left hand so they are perpendicular to each other. The forefinger points in the direction of the magnetic field. The middle finger points in the direction of the current. The thumb will then point in the direction of the motion or force on the conductor. The force is strongest when the current is at a right angle to the magnetic field. Application of Fleming's left-hand rule. Question. An electron enters a magnetic field at a right angle. What is the direction of the force on the electron? Solution. The correct answer is D into the page. According to Fleming's left-hand rule, the force is perpendicular to both the magnetic field and the current. It is important to remember that the direction of conventional current is taken as opposite to the direction of the motion of electrons. Therefore, the force is directed into the page. Electric motor devices like electric motors, generators, loudspeakers, and microphones utilize the interaction between current-carrying conductors and magnetic fields. Structure of an electric motor. An electric motor consists of a rectangular coil of insulated wire, ABCD, placed between the poles of a magnet. The ends of the coil are connected to two halves of a split ring, P and Q, which are attached to an axle. Stationary brushes, X and Y, make contact with the split rings to supply current from a battery. Working of an electric motor. When current flows through the coil, Fleming's left-hand rule can be applied. The force on arm AB pushes it downwards, while the force on arm CD pushes it upwards. This causes the coil and axle to rotate. After half a rotation, the split ring commutator reverses the direction of the current in the coil. A commutator is a device that reverses the direction of current flow. In an electric motor, the split ring acts as the commutator. Continuous rotation. The reversal of the current also reverses the direction of the forces on the arms AB and CD. The arm that was pushed down is now pushed up and vice versa. This process repeats every half rotation, resulting in the continuous rotation of the coil and the axle. Magnetism in medicine. The human body generates weak electric impulses carrying through the nerves can produce a temporary magnetic field. These fields are fragile. 1/1000th of the Earth's magnetic heart and brain can produce a significant magnetic field. The magnetic field inside the body is used to obtain images of body parts. This technique is called magnetic resonance imaging, MRI. These images help in medical diagnosis. Electromagnetic induction discovered by Michael Faraday. Whenever there is some relative motion between the magnet and coil takes place, then electricity is produced in the coil. The first was studied by English experimental physicist Michael Faraday, 1831. He discovered how a moving magnet can be used to generate electric currents. Fleming's right-hand rule. The induced current is the highest when the directio of motion of the coil is at right angles to the magnetic field. In this situation, we can use a simple rule to know the direction of the induced current. Stretch the thumb. The forefinger indicates the direction of the magnetic field. The thumb shows the direction of the motion of the conductor. The middle finger will then show the direction of the induced current. Electric generator. The principle of electromagnetic induction can be applied to produce large currents for use in homes and industry. In an electric generator, mechanical energy rotates a conductor in a magnetic field to yield electricity. An electric generator consists of a rotating rectangular coil, ABCD, placed between the two poles of a permanent magnet. The two ends of this coil are connected to the rings R1 and R2. Their inner sides are insulated. Structure of an electric generator. Two stationary brushes, B1 and B2, are kept pressed against the rotating rings, R1 and R2. The axle is mechanically rotated from the outside, which in turn rotates the coil within the magnetic field. The brushes are connected to an external circuit, often with a galvanometer to detect the current. Working of an electric generator. As the coil rotates, say clockwise, the arms A, B, and C, D move through the magnetic field, and an induced current is set up in them according to Fleming's right-hand rule. This creates a current that flows in the direction A, B, C, D through the coil and from B2 to B1 in the external circuit. Alternating current, AC. After half a rotation, the direction of motion of the arms reverses. Arm CD moves up and arm AB moves down. This reverses the direction of the induced current in the coil, which now flows in the direction DCBA. In the external circuit, the current now flows from B1 to B2. This type of current, which changes direction after equal intervals of time, is called alternating current, AC. A device that produces this is called an AC generator. Direct current, DC, is a type of current that always flows in one direction. To produce DC, a split ring commutator is used instead of full rings. This ensures that one brush is always in contact with the arm moving up, and the other with the arm moving down, resulting in a unidirectional current. This device is called a DC generator. In India, the AC supplied to homes changes direction every 1/100th of a second, which corresponds to a frequency of 50 Hz. Domestic electric circuits. In our homes, we receive a supply of electric power through a main supply, also called mains, either supported by overhead electric poles or by underground cables. One of the wires in this supply, usually with red insulation cover, is called live wire or positive. Another wire with black insulation is called neutral wire or negative. In our country, the potential difference between the two is 220 volts. At the meter board in the house, these wires pass into an electricity meter through a main fuse. Through the main switch, they are connected to the line wires in the house. Household circuits and earthing homes often have two separate circuits: 15-amp circuit for high-power appliances like geysers and air coolers. The other circuit is a 5-ampere current rating for bulbs, fans, etc. The earth wire, with green insulation, is a safety feature connected deep into the earth. It is connected to the metallic body of appliances to provide a low-resistance path for any leaked current, preventing severe electric shocks. Diagram of a domestic circuit. This slide shows a schematic diagram of a common domestic electric circuit. It illustrates how the live, neutral, and earth wires connect from the main supply to a distribution box with fuses and then to various outlets in the house. In each separate circuit, different appliances can be connected across the live and neutral wires. Each appliance has a separate switch to on, off, the flow of current through it. Each appliance has an equal potential difference. They are connected parallel. When the live and neutral wires come into direct contact, it causes overloading. This occurs due to damaged insulation of wires or fault in the appliance, accidental high voltage, connection of many appliances to a signal socket, short-circuiting and fuses. When overloading happens, the current in the circuit can increase abruptly. This is known as short-circuiting. An electric fuse is a safety device that prevents damage from such high currents. The high current causes the fuse element to melt due to Joule heating, which breaks the circuit and stops the flow of electricity. Thank you for learning with us.